Good morning, good afternoon, or good evening, depending upon where you live around the world. I often will say, oh, I've done enough now, I can't add any more, that's the end of it. But that quite often leaves me unsatisfied, as this has in this case. So, here's another video. One of the things I mentioned was about the scaling and how we can use different methods within SketchUp to achieve a particular size. One way of doing that was the ratio between the length of the area that we want to cover and its diagonal. And we know that there's a ratio of 1.414 per meter for that. And I'd written down that ratio. So I use it all the time within the building if I'm doing squaring of a building or pitching a roof, etc. But in this case, we can use it at the very beginning and achieve both our base and our diameter for our dome. And rather than having to use the ratio, we actually use the physical dimension of the base straight away. So most of the domes I've been working on of late have been around the 8 meters, a 6 to 8 meter dimension for the base. So I'm going to have an 8 meter dome, base. So all we need to do is create a 8 meter by 8 meter rectangle, or square. Make a group. We know that this would be a multiple of 1414, 8 times 1.414, but it also, if we just rotate that now, becomes our diameter for our dome. So if I move that, if I find the halfway point for it, there we go. If I put it there, move it off in the green axis to the center, I know that that is the diameter for this dome. Am I right? Well, if I'm not, you'll never get to hear this video, or watch this video. So there's the center, I come out, and that would be the diameter of the dome. However, it's not the location of the dome yet, because we're using a partial segment of the dome. It's not a full half dome. We need to find where the heck that will lie. How do we achieve that? Interesting. So that's what we're going to do next, and then we'll drop this down. So bear with us, and we'll achieve that end goal. Well, in fact, we don't have to worry about that, not yet, because the end result will determine which leg type we will be choosing. And this one, in this case, is the shorter leg type. But leaving the situation, or the setup as it is now, we would be creating the longer leg type as shown in the other videos that I've done. Now, so what we need to do, however, is to alter the domes, or the circumference, so that it is a 16, or in this case it'll be half, because when I go to click this, I'll show you what I'm talking about. When I go to click that, because of that line that we put in earlier, it divides the circle into half. So when we click the info, it shows that the way it was drawn was a 12 segmented half circle. We want an 8 segment circle, because we use the 4V, 1, 2, 3, 4, the 4V, 4 frequency dome. And just for consistency and clarity, I'll change that one also to an 8 segmented half circle. Now that's irrelevant. We can actually delete the bottom half because we won't be using it, but just for the moment we're just leaving it. And because we know that the way we divide off the circle to generate our dome, we go to the second point here, and we can put a vertical line down, which of course matches that intersection, which is nice to know. Now from there we can create our dome, and by using the method that we've shown here. So if I'll just rotate this through the horizontal 90 degrees, and we can put another one in if we want. Well, we will want, so that we can get our points for the hexagon and the height. Well, no, that'll be generated off the sides, and for our lower leg. Okay, so I might just do that right now. Always can hide it. Rotate 45. You can either use the physical model itself to rotate round to this point, which we note is exactly intersecting there, again reinforcing that your drawing is correct. Or for the rotation, as I prefer, don't always do it, but as I prefer, typing in the amount in this area here, so that it's more likely to get a precise rotational distance than when you draw here, because you may pick up a discrepancy that you're unaware of. Okay, now we know for the way we are using this Heath Robinson approach to drawing a dome, that if we join those 3 points, we wind up with the first part of the squashed pyramid, or the top for the dome. What is the next one? Well, that has to be, for my purposes, the leg. So how do we generate where we choose the leg? So we've got the very bottom point there, but as we zoom in here, I've cheated on this one. Instead of putting the rays of the diameter, I've rotated that circle so that it goes round 1/2 of one of these segments, which is allowed, I think, is 11.3 degrees, if my memory serves me well enough. Sorry for my laugh. So all we do there is, on that face, we go to rotate it, make sure we've got this sort of rotation tool, find the halfway point on one of the sections, rotate round until you meet that corner. Don't worry about there's the difference there, and then that point there becomes the line around which, or from which, you will draw the strut. Now, to do that, take a parallel line there, and somewhere along this line will be the length of the strut. How do we achieve that? Well, very easy, in fact. We go from here out along the red axis to that point, and down, back in, and we've created our plane through which that guideline would penetrate. Let's achieve the other side of it. I rotate. All I need to do now, 1, 2, and 3, get rid of those. We don't actually need those. And we've created our bottom of our leg, Now, by rotating the circle, I've created a point where the hexagon can be generated. and from there we can line it, draw in our other surfaces. And because it looks quite, I'll get rid of the guide, because it looks rather squished, I think it's a lot to do with this leg. You can, and just as an aside, I'll hide that. Hide everything else. You can see that it's actually quite leggy, and there'll be quite a high degree of angle or change in there. So there's a lot of thrust, the moment of rotation in this area here. So I'm a little bit concerned that there is a kind of a get round. There's a couple of get rounds or go rounds. Most of the structures that you'll see, that energy or that force will be eliminated or countered by the strength of the hub. But if you're not using that hub approach and you're just using the triangles and how they all meet together at this point, you create this triangle, you create this triangle, etc., and you join them all together, that moment of rotation needs to be taken up by how well you fix the two triangles together. I'll talk more about that later and how we can mitigate that. Okay, I'll just unhide everything again. I will just pause the recording and save these, which I have done. I've saved the surfaces, grouped them into the quadrant here, rotated it to create the dome. Again, I like looking at this line here, because I find that in a lot of the other photos, that this is what you'll see when they create their physical model and they take shots of it, and you can see the curving nature of that particular line of surfaces there. Knowing that, I feel comfortable that this is at least a way to follow how they've done it now. They've used a different method, which I'm almost certain they will have, where at least following close in their footsteps. That we've got a big difference in our distance here for this strut, for this length of strut compared to this one. It is what it is. But what we're doing is we're using a geometry-based, the physical shapes-based approach to achieving all our points. So I'm happy with that. I've scanned over some research papers on geodesic domes by people with greater capacity to understand that than me, and they talk about the different types of domes, how they be created, coordinate based, Cartesian based, and well, it's over the top of my head. All I'm happy with is that they know what they're doing, and they come to the conclusion that if you do it a certain way, it works. And one of the things they said, though, was that the different approaches will result in either lesser number of struts or less difference in the strut lengths. Seldom will there be the both. And the fewer the struts for most people, the fewer different lengths of struts, the better. One of the things that this shows up as, I would say, not a plus, but maybe just a physical reality of drawing a dome in the structure where the sides are in this plane, all the points line up into that one plane, is that you wind up with these discrepancies. So you've got a relatively short strut length there, but a relatively long one there and here. So that's not ideal, because it would be better if the struts were of more closely related lengths. It is what it is. We can't cater through this method to eliminate that. We may be able to fudge it by sliding the point up here, but how does that achieved? Yeah, so fudging it in the drawing program to suit an idea is less elegant than having something upon which you can draw repeatedly the same sort of dome, same structure. Get rid of that. So that's what we've got there. What I'm going to quickly do, I'll actually end the video here, is to draw, in fact I'll create the video for that, where we have a lesser length leg. Now what is that lesser length? Well, it might be the length that this strut is. So whatever this strut is, we may drop that down and have that the length of this particular triangle. So it would, in theory, make that triangle and that triangle the same dimension. So that's one approach. Or we lift this plane upon which we generate that very bottom point for the creation of the leg. We can lift that up to the halfway point. And there's no other reason than it's just a physical point on our base structure, or a base upon which we draw the dome, to reference. I don't think there'll be anything magic about that. Of course, if you lift it up to this point, that leg's going to be really, really stout. It's going to be short and thick, a bit like me. Okay, that'll be it. We've gone a bit longer, over a quarter of an hour on this one, so we'll end it, and I will be back later. Bye.